Right. Oh. Screen went dark for him. No. Okay. Sorry for the inconvenience. I don't know why that went off like today.
Yeah.
Had a hold of IT and they're like, and they said, yeah, that went off and we're getting it rebooted here. But okay, so we were talking about matrix multiplication. Were you able to start to make sense of this equation?
I mean, I think something I can probably figure it out.
So we're just going to go back to this example. Yeah, so we're going to multiply. Oopsie. So now remember, you have to the k's have to be equal, so the columns of one have to equal the rows of the other, or else you can't multiply them. So if you multiply the 2 by 3, 2 rows, 3 columns, by a 3 by 2, three rows, 2 columns, you'd end up with a 2 by 2. So that'd be your IJ. So let's see how this works out. So we want we'll just start with trying to figure out what's the best way to explain this. Basically, what we're doing is we're multiplying row by column. So let's just look at the position. In this matrix, so we're multiplying 2 by 2, 2 by 2. 2 rows, 2 columns. And so we know it's going to have to come out of 2 by 2. And so in the first spot here, that's going to be our C11. So that means that's C row 1, column 1. Okay. So what that means is we're going to multiply row 1, column 1. And we're going to add those components together. So we're going to have 1 times 7 plus 5 times 4. And so if you think of your AIK, you take row 1, column 1, so it'll be A11. Your B then has to be so your K will have to be a 1, so that's row 1, and then J will be column 1, so it'll be A11. So then your next one, it'll be your A12, so it's row 1, column 2. And then it'll be, and then B will be 2, 1. It'll be row 2, column 1. Okay. So it's just, it takes a bit to kind of connect what we're doing to the equation itself. After a while, it just becomes secondhand. So then your next position is oh, that's not 2, 2. That's your C1, 2, row 1, column 2. Okay, so your row 1, column 2, that's going to be 1 times 3 plus 5 times 8. Now, the next one, bottom left, that's going to be row 2, column 1. So row 2, column 1 is going to be 2 times 7 plus 6 times 4. And then we have row 2, column 2. It's going to be row 2 of matrix 1, column 2 of matrix 2. So that'll be 2 times 3, 6 times 8. What we end up with is 27, 38, 43, 54. Okay, So I think the best way to start, that's how I started when I learned it, maybe it'll work for you. I try to look at each position. And so here. And that's just like my row one, column one position. I know that I'm going to be multiplying row one from the first matrix by column one of the second matrix. When I get to the row one, column two, I know that I'm going to do row one of the first matrix and the second column of the second matrix. So that's how I started. And eventually you'll be able to equate this to the equation above. Because again, if you look at this, so like say this was C1, 2, okay. So I has to be 1, J has to be 2, and then the K's will have to equal each other as you're going through. You're going to do so A11 times B12 plus A12 times B22. So that's how it's working. But I still think it's easiest for the time being to say, well, I have matrix 1, matrix 2. I'm going to do row 1, column 2. And that gets you started pretty well. Okay. Let's see if you can do it. So you see, so for what's the so matrix order? So what do you things I've been saying? What do you think the matrix order of that first one is?
3 by 3.
3 by 3.
Okay.
What about the second one?
1 by 3. 3 by 1.
3 by 1.
3 by 1.
Rows first.
Rows first. Okay.
So, and even though those don't necessarily look like rows, so that's a 3 row, 1 column, that's a 3 by 1. If you have a 3 by 3 and a 3 by 1, what do you think that'll give you?
By 2 and 3 by 1.
A 3 by 3 and a 3 by 1. So your K's are 3.
So that'll give you a 3 by 3, right? Or no, a 3 by 1.
3 by 1.
Okay. That's I guess so 1 times 2 plus -1 times 2 plus -2 times 2.
Not times 2.
Oh, I didn't move down the column.
Yeah.
My bad. So then -1 by 1 and -2 by 3.
There you go.
Okay. One divided by 1 plus 1 is 1. 3 by 2. 2. 3. Okay. The next. Negative 5.
You sure it's 4?
Am I sure?
See, so 4 plus 1 minus 3.
Is it -3?
Yeah,
My bad. I keep doing that.
hey, that's the thing. This is something you've never done before. It's going to take practice.
Yeah, I just have to keep track of it, I guess.
Matrix math is unique.
Yeah.
Once you get it, linear algebra is a lot of fun. And you're able to think in a way that nobody else can. And what I think is funny when students take this, they hear the word algebra, like, oh, that's going to be easy. And then they get in there like, this isn't algebra. What do you get?
-5 to 11.
Yep. So let's go ahead and write this down. So everything is going to be row 1, and we only have 1 column. So our first position is row 1, column 1. So that's going to be 1 times 2 plus -1 times 1 plus -2 times 3. Then our second position is row 2, column 1. So that's going to be 2 times 2 plus 1 times 1 plus -1 times 3. And then we have row 3, column 1. So it's 2 plus 2 times 1 plus 1 is 3. And as you said, this gives us -5 to 11. So there we go. That's why it's also helpful to take a look at what you have. And if you think in terms of I, J, and K, I have a 3 by 3, 3 by 1, I, K, K, J. You know that when you multiply these, your C, I, J is going to have to be 3 by 1 matrix. So I always find that that helps at the beginning to kind of have a map of what I'm looking for. Okay. Now that you've had your crash course in matrix math, we're going to start to talk about how it applies. So the reason this is important is all of your symmetry elements are based off matrices. You know, we've been talking about them as maps over multidimensional spaces. Well, now you're going to see it happen. And your basic equation is going to be your new coordinates. So it's going to be your new X, Y, and Z equals your transformation matrix multiplied by the old coordinates, which is just X, Y, Z. So what do we mean by that? Okay, so what I'm going to do,
This is kind of just like a complicated way of doing vectors, right? Kind of?
yeah.
Okay.
So I'm going to start by drawing draw water, and then on top of water, I need my 3 accents, X, Y, and Z. So then X will go there. Then there's your X, Y, Z, okay? Now, let's figure out what happens with all of the symmetry operations. So, okay, water is a C2V. Okay. So now what we're going to do is the first thing we have to do is what happens when we have a C2 rotation. Okay.
Or did you want an answer for that?
Well, I'm drawing it out. If you can beat me to it. So the first thing we know is that H2 and H1 are going to switch places. But that's not necessarily what we're worried about here. I know that when I rotate it, my Z-axis will stay the same, but my X-axis comes over here, becomes -X. My Y-axis now goes out the back and becomes -Y. Do you see that?
Yep.
So that's what happens in a C2.
So that's why you always set your primary axis to be Z? Okay.
So it's usually it's convention for a group theory, for at least molecular group theory, to set Z as your principal axis.
Okay.
So most of the time, so again, if you're ever having a hard time picking a principal axis, try to find the Z coordinate, because your principal axis will almost always lie along Z, and that's just the convention, so that then everyone's math is consistent. Because if you ever write an article, other chemists are going to want to be able to take this apart. And if you've done your own wonky math, they're going to go, what did this lady do? Maybe you want to be that person.
Maybe. I think about it.
So, okay. Now, we draw water again in its original conformation. So H1 on the left, H2 on the right. And then I'm going to draw my XYZ. Now, the symmetry operation this time is our sigma v. Now, do you remember which way the sigma v pointed, or which way it was oriented?
B is like with the primary axis, right?
Yeah.
So it's like it'll be halfway in between the hydrogens, right? Or no,
So
it's along.
Right. So your v prime goes between the hydrogens. Your v goes along the hydrogen bonds. Now we know that H1 and H2 are going to stay where they are. Now look, Z is going to stay the same. And so now this is why we're going to start putting this in. So if you go on Otterbein, you see all these X, Y's, Y, Z, stuff like so. This is your sigma V XZ. And so these will help you start to also differentiate between sigma V, sigma V primes and double primes. So your XZ is usually your sigma V, your YZ is usually your sigma V prime, so on and so forth. So this notation makes more sense now. Okay, so our Z stays where it is. Our X is also going to stay where it is. What about our Y axis?
Flip.
It's going to flip, it's going to reflect to the back. We're going to get negative Y. We have one more to do. We have to do the sigma V prime. Okay, so now we know that the sigma V prime is going to be the YZ plane. Okay.
I have no idea. You can like feel it through the floor. It's like, ow.
Well, that is a horrible drawing, but you get the idea. It's the YZ plane. So as I'm working on this, can you tell me what's going to happen to the coordinates?
Z and Y should stay the same, and then X
Mhm.
will switch.
So of course our hydrogens are going to flip sides this time. And right, Z and Y will stay the same because they were part of the reflection plane. And then X is going to flip to the other side. Now, so these are our symmetry operations. So now we have to start thinking about what these mean in terms of matrices. Okay. So the way we're going to look at a matrix, let me just do the identity matrix real quick. Give you an idea. Okay. This is your identity matrix. Seeing as how we have ones down, and that's called the diagonal matrix, and zeros everywhere else, what do you think that means?
That's just like X, Y, Z.
It is. So, and the way you can really kind of look at it is X, Y, Z, but also X, Y, Z.
So they're all pointing like one in
Yep.
their positive direction.
So if you look here, when you do with identity, your one means that whatever this operation does, the X component is going to stay the same, the Y component is going to stay the same, the Z component is going to stay the same. That's identity. But let's think about our C2 rotation. Let's go back up and take a look. So what happens, Z stays the same, so that'll get a 1. X and Y flip, what do you think they get?
Negative.
Negative 1. So this is going to be -1, -1, 1. Fill in your zeros. That is your C2 rotation matrix. Now, the great thing you're going to find out is as we go through, every single symmetry element so your symmetry elements are going to have common rotation matrices. That's why you really only need to look at certain molecules to get it set up. Because then as you go through the same kind of symmetry element in another point group, another molecule, it's gonna have the same rotation matrix. Okay. Let's look at sigma V. X and Z stay the same, Y changes. So what do you think that's going to look like?
Wait, sigma V, we're gonna see
So Z will go to Z.
-1 and 1.
Y will go to -Y. X will go to X. Okay, so your sigma V then going to be 1, 0, 0. Then -1 there for the Y component, and then a 1 there. Are you starting to see now how these are mapping in actual space?
Yeah, I get it.
And so, of course, we also said this is our sigma XZ. Okay, and then sigma V prime. Now let's see. Z will stay the same. Y will stay the same. X will go to -X. So this one let's see, we're going to have -1, 1, and 1, and then your zeros. So these are for your C2V here. These are your nice matrices. They are going to get a bit harder. Now, what I want to do is test the one of the rules of group theory. Remember, so the product of any two elements in a group yields another element of the group. So, for example, let's say we're going to look at C2 times sigma V, that's going to equal sigma V prime. Can you prove that?
With the matrix.
Yep.
I suppose we could, huh?
So our C2 and I'm going to set it up with you, but then let you work on it for a minute. -1, 1. Times your sigma V, 1, 0, 0, 0, -1, 0, 0, 0, 1. You have to multiply those two matrices.
Okay.
You need to see if you get the sigma V prime out of it.
So I guess.
Oops, we're supposed to do that on the next slide, but okay, we'll just do it here.
Great.
So what I'm going to do is I'm going to go ahead and cut this and drag it to the actual exercise slide. There we go.
Yeah, I think I did it.
Okay.
I got the same as sigma V.
Well, then that would mean you did it.
V prime, so.
Nice. So let's take a look here. We know we're going to produce another 3x3 matrix. These are both 3x3. So let's just start. We have the row 1, column 1. And in reality, this will be -1 times 1 plus 0 plus 0. Row 1, column 2, 0 plus 0 plus 0. Row 1, column 3, 0 plus 0 plus 0. So again, because like if I'm taking that row 1, multiplying by column 3, I'm going to get 0, 0, 0. Okay, so then row 2, column 1, 0, 0, 0. Row 2, column 2, 0, -1, -1, 0. And then again, 0, 0, 0. Now for row 3, I'm sick of saying 0, so I'm just going to write it. And then we're going to have the row 3, column 3. And of course, what this gives us is -1, 1. Yep, yeah, that's right. 1.
Yay.
So solidifies the group theory a little more. Because I mean, we were able to do it graphically by just looking at the rotations. But now you can do it mathematically by looking at the matrix elements. Okay, now, the thing we're going to do next is I'm going to show you a C3 rotation matrix. It's also going to key you into why in like a C3V, you get a symmetry element of E, which is like a 2-dimensional symmetry element. Because the rotation matrix is not restricted to the diagonal alone. Okay, so, and this will also help you understand why we're not going to go through and find higher order matrices. You're going to go, I don't want to. Okay, now let's think about we're just going to think about ammonia, looking top down on it. The C3, we're going to rotate through an angle theta, which is going to be 30 degrees. Now, let's think about, no, not 30, 120. They do that. 120 degrees, there we go. It's 360 divided by 3 to C3 axis. Okay, so let's try to think of this graphically. What I'm going to do is I'm going to start with a vector, so a position vector in the first quadrant, okay? This here, you don't know what it is, it's some angle 5, okay? Now, I'm going to rotate this through the 120 degrees, which, let's see, which should put it, I'm just going to eyeball this, it's not to scale. I don't know, let's say somewhere around there. Those don't even look the same length, do they? Let's try, at least try to make it look halfway decent. Yeah, that'll work. And so then what we have is we have our position vector R and our second position vector R prime, because the first one is at X, the first point is at XYZ, the second one is at XYZ primed. And the first thing we want to take, we just want to remind ourselves of that the magnitude of R equals magnitude of R prime, so R equals R prime, that's gonna help us in a little bit. Because again, it's the same vector, so it's gonna have the same, we're just rotating it to a new place. But we're rotating it through, of course, our angle theta.
So it's like when we do a little rotation and we put H3 in H1's position.
Yeah,
And
and so to help you out here, imagine right here in the center what this is. That's our C3 rotation. Now, the first thing I want to do start taking into account position vectors. What's up?
Have you posted the test yet?
Well, when I finish getting them graded, I will.
No, like.
Oh, no,
for
no,
me to take.
no, not yet.
Okay, when can you post that?
As soon as I'm done here.
Perfect.
Mhm.
Thank you.
You're welcome. So we have Rx and Ry. And so let's just go ahead and write out what these are. Let's see if I can write these in the way I want to. So what I'm going to call these is X. That's going to be R cosine of phi. Y going to be R sine of phi, because we'll be able to plug those in later. We'll just be able to plug in X and Y. Now, let's figure out what X prime and R prime are. Okay, and the reason we're doing this is because, again, this is at X, Y. Okay, so that's why we call X is R cosine of phi, Y is R sine of phi. And of course, as we said, this up here is X prime, Y prime. Okay, so what is X prime?
Is it just the 5 plus 120 degrees?
It is. So I'm going to start by saying R prime. I'm only going to do this once so that we can just have it as a record. So phi plus theta. Okay, that's the way we're going to write it. Now, we remember, based on the fact that R equals R prime, X prime is going to equal R cosine phi plus theta. So then that means our Y prime is going to be R sine phi plus theta. Did you ever think you would do this much trigonometry again?
Probably not.
Okay, now we're going to use some trigonometry identities. These are things you can just look up. Usually, okay. I mean, I know I'm a mega nerd, but like if I'm ever doing like theoretical work or physics work, I always have a table of trig identities pulled up because it can help you simplify a lot of stuff. Okay, now our trig identities. Cosine of alpha plus beta. That is going to be cosine alpha, cosine beta, minus sine alpha, sine beta. And so right now you may be going, how is this going to simplify everything? Then your sine of alpha plus beta. And this is why we like tables. Mathematicians work this out already.
Yeah.
We don't need to rework that identity.
Agree.
Sine alpha, cosine beta plus cosine alpha, sine beta. All righty. So we're going to use those identities on X prime and R prime. And now, let me go down here. So our X prime, I'm going to go ahead and skip a step because once you work this out, both of those will have a multiplier of R. So I'm just going to pull R. Well, we don't even have to think of it like that. I'm just going to put R out front, and then I'm going to fill in what cosine of phi plus theta is. So it's cosine of phi plus theta, so that's going to be cosine of phi, cosine of theta, minus sine of phi, sine of theta. And then I'll do y prime, r is out front, we're going to fill in the sine of phi plus theta. Sine of phi, cosine of theta plus cosine of phi, sine of theta. And the reason I'm doing this is most textbooks just show you the C3 rotation matrix and they go, you figure it out. And I'm like, no, let's not do the figure it out.
Yeah, I probably wouldn't have guessed that's how you do it personally.
Now, we're going to play with some grouping. Okay, we're going to multiply the r's in. And when I do that, I'm going to do grouping like this. Okay. So even though I put the brackets in there for grouping, does it make sense what I've done so far? I've multiplied in the r's, and I've just split the trig functions apart by simple grouping, because what you notice, I can put in x and y now. So we're getting x prime and y prime in terms of the original x and y. And so that's going to be x prime is going to be x cosine of theta minus y sine of theta, and then y prime. Let's see. So y cosine of theta plus x sine of theta. And I want to go ahead and just flip this because I want my x and y to be on the same side of the equation for certain reasons. Sine of theta plus y cosine of theta. Now, there's a reason we're not including z in this. Because think that we're working on the matrix for a C3 rotation.
So the Z will not.
It's not gonna, Z is gonna get a 1. Okay, now, here's what we do with linear equations, okay? So the first thing we're gonna do is we're gonna say, we can take x prime, y prime. That's going to equal the matrix x cosine of theta minus y sine of theta over, and then the second element is going to be x sine of theta plus y cosine of theta. And so this is a 2x1 matrix. And we can actually decompose this to form, let's see, cosine of theta, sine of theta, negative sine of theta, cosine of theta times the matrix xy. So we've hit on something that you can actually just look up and use in the future. But you see this first matrix here with the trig functions? This is your standard rotation matrix. So it's usually like r theta. That is just a standard rotation matrix, and you can look that bugger up. But what it tells you is if we look at the C3 rotation, you can imagine we have to have a matrix that rotates multiplied by the XYZ. What that tells you is the C3 rotation matrix, you're going to have cosine of theta, sine of theta 0, negative sine of theta, cosine of theta 0, and then 0, 0, 1 for Z. That is our C3 rotation matrix. Usually we don't leave it in terms of theta, because what, 120 degrees? That is 2 pi over 3 radians. Okay, so usually what we then will denote the actual C3 matrix as cosine 2 pi over 3 sine 2 pi over 3 0 negative sine 2 pi over 3 2 pi over 3 0 and then 0 0 1. Because we already know what theta is for C3. This is the way I usually denote it. I want you to also know that you can replace all those trig functions, and some books do this. Cosine of 2 pi over 3 is a negative 1/2. Negative sine 2 pi over 3. That's the negative square root of 3 over 2. Sine of 2 pi over 3, that's going to be the square root of 3 over 2. And then, of course, our cosine again. So you could put in these fractions from one of those trig locations. And some books do that, and that's perfectly fine. Just know that that's where it's coming from. Well, now you have the C3 matrix. So the other elements for a C3V, of course, your identity, your E, which is a diagonal of 1, 1, 1. But take a look. However, C3V also has several sigma V's. Which is going to equate to an original CVXZ. That's just your first one, and you have all these equivalent sigma V's based off their location. And we know from group theory that in this point group, it's still 1, 0, 0, 0, minus 1, 0, 0, 0, 1. So we don't have to do the whole XYZ thing again. Sigma V's are going to be common. So it's a common rotation matrix. Okay. How long have we been going for?
I have no idea.
No, we're at about 50 minutes now.
Do you want to get through the rest today? I'm not doing anything.
Well, let me just let's go on. Let me start explaining characters to you. Okay. Characters. So this is where we're going to start building what we call a character table. So your symmetry operations, initially, they're going to be the trace of your matrix. Okay. I want you to try to tell me. I'm going to give you two matrices here. See if you can tell me what the trace. Oh, darn it, I put it in there. Well, so if you can't tell me what the trace is, you're not having a good day.
And what are traces?
It's an operation you can perform on a matrix. And it gives you information. Oops.
Okay. Maybe I'm having a bad day, I don't know. I don't know what that means. The sum?
Mhm.
Oh, okay.
So for your E, 1 + 1 + 1 = 3. So that's going to give you your character 3. And what I want you to start realizing is the notation for this. So again, if you're ever reading and you see it, so it's the Greek letter chi. They use that to represent character. For your C2, -1 - 1 + 1 to -1. And you could do that for the sigma V and the sigma V prime as well.
I see, okay.
You can relate those back to when we were doing the rotations of the axes. So, but let's look at something. So our sigma V prime, okay? I want you to tell me what might be going on here. In our sigma V prime, I should number that down a little bit so I have room for it. Our sigma V prime is, of course, the YZ. Okay, and so we know yes, of course, Z will stay the same. And Y will stay the same, but X flips to -X and H1 and H2 trade places. Okay. But then let's look at the character up here. The sigma V prime, 1 indicates symmetry. So 1 would indicate that nothing happened, but we see very clearly something did happen. It looks more like a -1 than a +1 because the H1 and H2 switch places. Okay, well, that tells us that this does not fully represent what we need. So we're going to need an expansion of some kind. So what you're seeing here, when you do the trace of all of your rotation matrices, this gives you what's called your reducible representation, which is represented by capital gamma. Your reducible representation of this point group is a 3, -1, 1. So we're going to need an expansion. So what we can do, wow, I thought I would take more room than that. Okay. What we need to find now, the character tables are made up of what's called irreducible representations. We need all of them. Okay, so here is a start. All right, so you see the reducible at the bottom. And then up top, you're going to start to see irreducible representations. And so let's think about where these come from. Let's look at our C2 matrix. I'll go ahead and put up sigma v as well. So now look at the irreducible representation. What do you, can you tell me where those numbers are coming from?
It's like we made a matrix of the matrices.
We did. So all of those are the diagonals of your matrices.
Okay,
Okay. Okay, so we have 3 of them now. And what we can do is we can start to build our character table. Now, these are 3 of the irreducible representations that form this the C2V group. There is one missing, so we're going to have to expand and figure out what it is. So what we're going to do is we're going to start going through rules for character tables. Okay, so the first thing you want to know for a character table is its order, and the order is H. So to determine the order of the group, you simply total the number of symmetry operations. And so up at the top, you see I have 1E, 1C2, 1 sigma V, 1 sigma V prime. That's 1 plus 1 plus 1 plus 1. That's an order of 4. The group order is 4.
so you might be missing your other C, wait, no, you're not.
So in others, you'll see like you'll see 2 in front of a C3. So that would be 2 of those.
Okay, yeah, I get.
So this one is just all coefficients of 1, and there you go. Now also notice on the left side, what do those look like?
They look like vectors, they look like scalar.
Oh, no, look at the far left column.
Yeah. A1, B1, B2.
Mhm.
I don't know.
We worked with those earlier. Those are our Mulliken symmetry designations.
Mulliken symmetry designation.
Remember when we were assigning to the, like we did that in the last chapter?
Okay,
So now these are coming back with a vengeance.
I see, okay.
Okay, so as time goes on, you'll start to make more sense of this. Now, we will end up, once we get full character tables, we will end up talking about, it's one of them. I'll look it up and I'll get the answer for you. You see the XYZ denoting each one of these? So each one of those irreducible representations, the XYZ, that when you see the XYZ like that, that denotes one of your spectroscopic vibrations. So I'll look it up and remember which one it is, but now you can see the symmetry of that spectroscopic vibration.
Okay.
So this is how you're going to, so as we grow these, you're going to start to take these apart and learn more about them. Symmetry operations are arranged in classes. So all operations in a class have identical characters for their transformation matrices. So we talked about that. So like your sigma V's are all going to be the same. So you see how and then a class, like a class of C3, you have the same rotation matrix. It doesn't matter how many times you do it. Your first C3 is that matrix. Your second C3 is that matrix, so on and so forth. And so, so the four columns of this represent the, so these are the symmetry operations. Therefore, C2V has 4 classes of symmetry. Okay, so we'll continue. So yeah, that gets us to about an hour. Yeah, close. So we'll continue on from here tomorrow. And we'll keep learning about these symmetry elements and classes and character tables. See if we can use these elements of character tables to see what irreducible representation is missing from the C2V. We'll have to find it. There's one more.
Okay. The secret one.
And they pop up because you can get a lot of these from rotation elements, but then you can also say, well, all of these rules for character tables, there's got to be one missing because it just doesn't match the math, and you can find it. But also, do you see the C3 here?
Yeah.
Can you start to see why it's going to have a 2-dimensional symmetry? Why it's going to have an E?
Yeah, because you're
getting off diagonal elements.
yeah.
So
I see it.
more off diagonal elements will take us up into like tertiary symmetry and so on and so forth.
Fun stuff.
Oh yeah, we'll just keep plugging away at it.